So let's get started, and I'm gonna start recording. And all right, everyone. So today we are going to talk about viral diagnostics. So means can we detect for kind of medical diagnostic system? Again, this is something usually I discuss in PME 410 instead of this class, but this year I think it's timely and it's important for us to think about. And for many of us, I guess we all will be biomedical engineers. And so in certain, in the current situation, I think it's important for all of us to think about what we learn, whether we can actually help the current situation or in the future any more future outbreak that may potentially happen. And I guess not only for biomedical engineer, right? For any type of engineer, if you are a computer engineer, are you thinking about how do you get better software to do online communication, online teaching? So if you are you do manufacturing or industrial engineering, so you think about how do you increase the production of some of the very needed maybe PPE, some of the product. Of course, for biomedical engineers, so we are certainly in a important position of to kind of dealing with some of these medical crises that include a lot of problems and so at the end, I think engineers are really a discipline that we try to helping people, helping the environment, helping everything. So first, we particularly important for us to think about this right now. Anyway, so in particular, I'm going to talk about in general how viral diagnostics, so all kinds of diseases caused by viruses, how we detect it. It's, of course, we particularly use COVID-19 as a particular important example, and also very important for us to think about. I think very likely. I don't know what will happen in the economy in the next few years, by the time we graduate. But one thing will happen for sure is that there will probably be more resources and interest in develop diagnostic system. So I think that may be a good time for us to all learn a little bit about how medical diagnostics are done. All right, so anyway, so let's go get started. So before I get started, so there's some references you may be interested to take a look if you haven't come across to that so far. So so there's some, of course, a lot of things we can learn from Wikipedia nowadays. They do have a good summary of some of the laboratory diagnostics techniques for viral infection. If you want to learn more about for COVID-19, so WHO actually have some of the guidelines putting in their website to kind of talk about so the technical guideline for sort of laboratory guidance for COVID-19 detection for humans. And so we also find there's actually some websites out there. There's so many of them out there nowadays. So, but some of them actually kind of keep track. Some of the commercial available COVID-19 tests. If you're interested to see what's out there, what has been approved, what the trend of people doing, maybe that's a good idea to look at some of this website. So there are actually a lot of different news article, research article every day that kind of talk about different aspects of biomedical detection related to COVID-19. So this particular one kind of I think is maybe good read. The interest to go ahead to take a look at these references. Talk about how fast portable tests can kind of they play an important role in coronavirus pandemic. Okay, so if you read the news nowadays, probably you see a lot of different discussion about some of the rapid testing is important for combating some of these infectious diseases. You probably hear a lot of discussion in terms of do we have enough testing? Are we testing enough people? And so also kind of a lot of complaint from different people saying, oh, we don't have enough diagnostic, we don't have fast diagnostic that we need to efficiently isolate the patient to identify who are the carrier of the viruses. And so there are a lot of discussion on there. So, and there's some article you may see, they talk about, oh, why it takes so long for us to get the COVID-19 test result. And also you see some of the news highlights say that, oh, they have certain new technology come on board, and so that could be a game changer for everybody. And so almost every day you see kind of different people discuss what kind of technology are being developed and what's being approved by FDA. Sometimes you see, oh, I found one that's for rapid coronavirus detection approved by the FDA. So that test give result in as short as 45 minutes, and then tomorrow you see another one saying that, oh, there's one kind of have a blood test to screen coronavirus, but there's some limitation we should consider. So I think as for all of us, biomedical engineers, and maybe I think it's important for us to at least take a look at what are this technology about and how it is done, whether there's some limitation in some of this technology and what can be done in the future, maybe for the current pandemic or maybe even for some of the future potential outbreaks that we may foresee. So I think that's kind of one of the motivation, but I think for now, everybody kind of aware the importance of rapid diagnostics is important. So, all right, so let's talk a little bit about the basics, about what are we really dealing with. And if you watch the news or read the news article, a lot of time people call coronavirus. But actually, the disease we are dealing with, we are kind of in this pandemic is actually called COVID-19. So it's really mean coronavirus 2019. And so it's basically infectious disease. So the virus that caused this disease, that caused COVID-19, so the full name is actually SARS-CoV-2. And means what? Coronavirus is actually a broader name that describes multiple viruses that infect different species. So there's actually 6 known species of human coronavirus. That so means there are actually more coronavirus that will infect other animals. But there are actually 6 known species that actually infect human. And one of the species actually have subdivided into 2 different strains. And so that's the SARS-CoV-2. So the SARS-CoV or SARS-CoV-1 that was originally identified in 2003. So that was very serious in Asia. So, but the one we currently dealing with technically is called SARS-CoV-2. Of course, in the news article, people keep calling coronavirus. And there's also another very important called Middle East respiratory syndrome. There's another disease also caused by another species of coronavirus called MERS-CoV. And so the 3 most infectious or most the worst one are really SARS-CoV-1 or SARS-CoV-2 that we're dealing with, and this MERS-CoV. So actually there are other known human coronaviruses, including some of the strain called Hong Kong U1, OC43, 229E. So those are relatively mild. So those actually, they're still causing some of the respiratory infections. And but those are more considered as common cold. So, but actually there are a lot more known coronaviruses that they carried by other animals. So far they're not known to infect humans, but that can potentially be. In fact, there are a lot more viruses. So if we look into exactly what's this SARS-CoV-2, is actually an envelope virus. When we say that means the virus is actually surrounded by this kind of membrane, actually lipid membrane. So it's the same lipid membrane in human cells. And of course, they have also this spike. So some of this glycoprotein S, and so that actually, that's how we get the name of coronavirus. And but effectively, SARS-CoV-2 is actually a positive sense single-strand RNA virus. So when I say that means this is an RNA virus, so the genetic material is actually carried in the form of RNA. When you say is positive sense, means when it get into the cell, the whole cell, it can directly start the translation process. It's, the telephone is almost like you have a messenger RNA. So it's a positive sense RNA, so that can translate and give create protein right away. So when I look at the RNA, it seems there's still kind of report quite large range in terms of the number, but I think the diameter of the SARS-CoV-2 virus particle is around 120 nanometers. So it's, so it's kind of a typical size of a virus. So you can find the whole genome in NCBI. So if you go search it, you can actually find the whole genome of this SARS-CoV-2 virus. And it's actually relatively large virus. So it's something like 20 or almost 30,000 bases. So it's, again, it's a single-strand RNA virus. So we can have some of these pictures of the coronavirus with some of the spikes surrounded by the membrane, and the inside is actually the nucleic acid of the virus. All right, so that we have some basic idea about this coronavirus. And so then the question is, how do we do viral detection? How do we detect viruses, especially we're dealing with some of the diagnostics? How do we do that? I think in general, there are 4 major categories of method to do viral detection. So one of the more basic or classical method is actually called viral culture. And basically to see this virus that can cause infection, one of the most fundamental method is you take that fluid with the virus. It could be a body fluid or maybe some tissue. You directly add it to some of the cell. So that if the virus can infect this cell, if there's no virus, if they cannot infect the cell, means that it's likely, means that there's no virus can infect the cell. If the virus can cause infections, infects the cell, then the culture is positive. So so that means one of the most fundamental methods is you have some whole cells that you know the virus can infect. So by looking at whether the virus actually infects the cells, you know there's actually virus there. It's one of the most fundamental methods for us to handle and study viruses. Another approach to do that is, instead of testing a virus that infects something or not, is you actually try to detect some of the viral antigen. So for example, some of the viral protein. So if you have a antibody or something like this, you can detect. So you can use an antibody that with a specific tag, could be a fluorescent dye, could be other tracer, as long as you can look at that, that's fine. So then you can use this antibody to bind to the viral antigen, like some of the viral protein. So if you have a way to capture them, then you basically tell, yes, we see some of this viral protein, that could become an indication of, yes, we have that virus over there. So that's called viral antigen detection test. I think the more common one, actually we see, we'll talk about more details. So, but one of the most powerful way to do viral detection nowadays is actually based on viral DNA or RNA detection test. As you mentioned, so SARS-CoV-2 is actually a single-strand RNA virus, means if the way to detect this particular RNA sequence, so you will have a powerful way to detect RNA. So it could be DNA as well, because of their DNA viruses. So, and means if you have a DNA virus, you can actually you want to use some of the method to detect DNA. So again, you may start with certain sample or other biological fluid. So then you find a way to detect this genetic material, again, to be DNA or RNA of a specific virus. So if you know the sequence of this DNA or RNA virus, then you will be able to design a test to detect the existence of this genetic material. So so this is actually a molecular specific way to tell whether there's what caused that infection. So compared to maybe viral culture, we do not know. So we know there's a virus can infect the cell. Okay, so it means they don't have much selectivity in terms of what we're detecting. Viral antigen has better selectivity, depends on the antibody you use to detect the viral antigen. And but if you have similar virus, they have similar viral protein, you may get a confusing result. So that's something to be careful. So in a sense, DNA or RNA detection test could be a very specific method for doing viral detection. So one of the tests that people talk a lot recently nowadays is some of the thing called antibody test. Means instead of detecting the virus itself, so there are tests people talk about to basically look at the antibody, means the host response. When somebody get infected by virus, so we actually we make antibody to fight this infection. This approach is instead of detecting the viral particle directly, we actually detect our host response. Do we have that specific antibody that fight with this virus? So that could give us an indication of whether the person was infected by this virus or not. So it's typically done by doing a blood test. If they find anybody, means that this person was infected. So by looking at the type of antibody, they can even tell it was infected recently or in the past. So we're going to talk about each method one by one. So something interesting to look into. So there's, again, I mentioned there's a website that actually kind of outlines, summarize some of the diagnostics tests. So for COVID-19 diagnostics tests, so this table clearly is not the full list. I just highlight some of the things. And also this table actually is updating every day. So every day they kind of engineer, big company, they step in so that's kind of just a kind of a brief overview. But I think it's something interesting to look at. If you look at all this name, right? Sapphire, Apple, Rose, BGI, all these major companies that you are aware of to do kind of diagnostic, they really steps in. They all in a sense, when this pandemic really comes in and everyone tried their best to address that. So the very first one, so each test have its own name because each company, they may develop more than one product that can do COVID-19 diagnostics. So, but something interesting is look at this regulatory status. So it means FDA, in what point they approve it and all. So they all kind of go through this called EUA, the emergency use authorization, is because of the current pandemic. And so the very first one was actually a CDC assay. This CDC 2019, originally it was called the novel coronavirus, so real-time PCR diagnostic panel. So that was one of the very first approved in the United States. Oh, I need to mention. So this list, I picked up some of that related to the US FDA, but there actually other in the Europe, in Asia, they all kind of different. So of course, they all kind of look at each other's. So, but when those companies develop new diagnostic tests, so they actually try to get approval from the Europe, in US. So, but one thing interesting, you see in the very first one was actually that was get EUA in February 4. So that was pretty early in the coronavirus outbreak. So actually, it was kind of first reported more in China. So that was in kind of late January. So they actually CDC already have a test in February 4th, and so they actually have an amendment in March 15th. So March 15 is around the time of our spring break, right? So that's the time we start to see a lot more outbreak in the United States. So they actually respond, they time to have an amend at March 15. So you can see around the same time, right, in early March or mid March, is kind of all these major companies comes in and start to have their tests approved. So I'm going to say this company probably have been working on this even right before this one, but that was kind of get the emergency use authorization from FDA. So one of the Roche is one of the early one in March 12. CRISPR diagnostics, a major lab test is in March 17. So ABOT 18, March 20th, Sheffield. So, but interestingly, you see all these approved technology are all based on PCR. So they're all based on detecting the nucleic acid. So I'm going to talk about the detail of it. So, and you probably hear some of the news on March 27th. So some people, this Apple. So they actually report a kind of platform that they can say it can be done as soon as 5 minutes, or but most of the time, if a negative sample, they take somewhere 10 to 15 minutes. So based on a related technology called isothermal application, and more recently, I think we start to see, I think April 1st. So we see one of the first tests that was called serological, means it's actually the antibody test. To look at the antibody instead of the viruses itself. So but that kind of take a little bit longer time. So in fact, this is only a partial list. There are a lot more tests have been approved in the United States and also in Europe, and people are actually using it one or the other. But I think it's interesting to think about what this thing was developed and how that evolved. Spans of time. If you probably remember at the very early of the outbreak, because at that time CDC was the only approved technology to detect coronavirus. So if you remember at that time, the news was kind of saying that some of the coronavirus cases, but they need to be confirmed, because at that time in the early March. So the only place that can approve to do that confirmation is actually CDC. So that's why at that time they kept saying, "Oh, we have a major kind of bottleneck." So we found all these patients, they have all the symptoms. They kind of, we say, even they may have done some tests, but the only approved confirmed method was actually by CDC. So that's why that present some of the bottleneck. And then later on, when all these other tests become available, they're approved by FDA. So then we actually expand our capability, our bandwidth to handle all these samples to kind of confirm some of these coronavirus cases. So we can kind of see how this big company actually start to respond to that outbreak as a bunch of time. Again, this list is still expanding. People are still developing new technology every day. So hopefully we'll get more and more available tests that are rapid and fast to use. So let's look into a little bit about some of the basic about viral life cycle, so the viruses. And I think it's some of the typical procedure or steps involved in the viral cycle is so viruses is something they have the genetic material, but they typically do not have the machinery to replicate. So in a sense, they always require some of the holes and kind of hijack their machinery to replicate themselves. And so usually start with a step called attachment. So kind of some of this spike and some of the receptor will bind to the cell. So means not all the cells, they don't necessarily infect all the cells. They're only certain type of cells, depends on the receptors out there. And so that's why I say in some of the viral culture method, you need to have a whole cell. If you know what whole cell this virus will infect, so then you have a way to handle that. So after this initial attachment, they recognize the whole cell, so they will go inside the cell. So of course, different viruses have different mechanism involved. But when they get inside the cell, so the main thing they try to do usually is replication. And so they try to amplify as, themselves as many as they can. So as I mentioned, coronavirus is a a positive sense RNA virus. So it means when it get into the cell, it's already behave like a messenger RNA. So it's already the RNA genome, so you can directly start to have translation. You can create different type of proteins. So after some of proteolysis steps, that cut into some of the specific protein. So something interesting about this single strand positive sense RNA is, yes, they will create some of the protein, including some of the replicates. And so that kind of eventually you kind of making the positive sense RNA to a negative sense. So then you can start to do more transcription to create more of that virus particle and also other viral protein. So after this replication process, including making the genetic material and some other proteins, so as shown in some of this messenger RNA, so express all these proteins. So then you go through some of this biosynthesis to create that protein, and also there will be assembly process. So that actually will assemble the virus. Of course, it will actually create more than one. So it actually will amplify many copies, and then so at that time, so then the virus will basically be released from the cell, and usually you actually kill the cell. So that's kind of a typical viral cycle. So let me see. Let me show you this video. Maybe we can learn a little bit more. Let's look at this video together. All right, so let's go back to our PowerPoint file. So give a basic introduction about viruses, life cycle. So as I mentioned, there are actually many different types of viruses, also saw in the video. So there are different way of classification of viruses. And one particular way is called the Baltimore classification. And in a sense, it grouped into some of the viruses that's maybe a single-strand RNA, could be a double-strand DNA, or it could be a single-strand DNA. So, but they also kind of look at the mechanisms of how the viruses replicate, especially how they make messenger RNA eventually. For example, some of the like herpesvirus, so this is how they call the type 1. So that actually is a double-stranded DNA. They actually directly make messenger RNA, like translation, transcription in some of the standard kind of process. So, but some of them may start with a double-stranded DNA in a forms of the single-strand RNA before they make RNA. So again, there are many different types. So hepatitis B is actually one of these double-stranded DNA. So although they're both double-stranded DNA, herpes virus and hepatitis B, but the mechanism involve how they make messenger RNA are different. Some of the very well-known one, HIV or AIDS, is actually also a single-strand RNA. And but the mechanism involved, they actually make some of this DNA RNA hybrid before they make double-stranded DNA again, before they make the messenger RNA. So the very important one, of course, the influenza that caused the seasonal flu and a lot of other avian swine flu and also Ebola. So those are actually also single-strand RNA viruses, but it's called lacative sense. Means the sequence is kind of the complementary to the sequence that actually make the messenger RNA and the protein. So that's kind of the called the lacative sense single-strand RNA. So that can actually make messenger RNA from there. So coronavirus means the SARS, MERS, COVID-19 that we'll be dealing with. Is a positive sense single-strand RNA molecules. It's called type 4. So the mechanism of messenger RNA actually involved making the complementary, the lacative single-strand RNA before it create the messenger RNA. So that's kind of for different viruses. So this is important for us to think about because of the method we use to detect DNA and RNA are similar, but they're different. So there's some additional step we may need to consider if you want to detect a RNA virus compared to maybe a DNA virus. So that's something we will talk more later on. But we can also see that some of the very common viruses that we deal with, they are actually in different categories. Okay, again, so one of the major method or the basic method people known to use is called viral culture. So one of the particular assay is called plaque assay. This plaque assay is basically you have a confluent monolith of cells. You will infect them by having loading virus with different concentration or different dilution. And then after that, you cover it with a semi-solid medium. Means what? You start with a certain tube of sample that there may be some virus. You want to know the concentration. What you do is going to do a serial dilution. You get basically 10% of that solution into a tube with another 90% of medium. So means this tube will be the 10% of the original one. So means 1/10 of the original concentration. Then you will take another 10% of the solution from this tube to the next tube, which will dilute another tenfold. So this can take you 2 dilution. So you will keep doing this. The process called serial dilution means every time you do you actually take 10% from one tube and then you lower it to another tube and add 90% of the medium there. So you keep diluting to a very low concentration. So, and then what you're going to do is you're going to load this sample into some of these cell culture dish or usually in some sort of multiplay formats. And what happened is means when you have a virus in the solution, it will actually infect the cell. When it starts to infect the cell, it will basically kill the cell, and it will also infect the cell nearby. So what happened is, if that's the case, so you will actually form a small, more like a small corner of small region of cells are being killed. So, and that's what people call a viral plug. This viral plug is formed when the virus infects the cell, but instead of infecting everywhere in the dish, you actually limit by putting maybe agar or some other cellulose. Basically, you prevent the virus can go to very far away. You just allow it to go nearby to infect the cells nearby. So that's how they form this plug. And then after that, you're going to sting. You can fix the cell, you can sting them. So the region without cell, because they're killed by the virus, will form this viral plug. So, and that's the region that you do not see a sting. So that's kind of an image of what we're seeing here. So the viruses, basically, it means probably there's one viral particle infect the cells there and then kill all the cells in that local region. So when you sting it, means you are able to count in this dish how many viruses are infecting the cells. And because they're locally limited by this agar or the cellulose, so that's why you can actually separate the effect of individual viruses. Instead, that actually gives us a way of knowing the concentration by counting the number of this viral plug. And of course, when you do a large dilution, you do high concentration, large dilution enough, you will not see anything at all. But you go to a kind of a little bit high concentration, you will start to see the number of this viral plug will increase as the different concentration. So by doing this, we will be able to actually extract to calculate what is the original viral particle load, the concentration of the virus you have in the original stock. So that's one of the very important methods for us to handle viruses. And a similar related method is called endpoint dilution assay. And so the idea for this approach is, you do kind of this serial dilution, but not all viruses may form this viral plug. Means that we may not see kind of a nice clean circle because it may not even kill the cell, but they just infect them. In that situation, you can still run a similar assay. So, but the approach is you load the virus there. You basically let the virus infect the whole dish or the whole well in a multi-plate format. So again, if you keep diluting enough, you will able to find a concentration such that you will not be able to infect any cell, because if you dilute enough, then you don't have a viral particle that can infect the cell. So in that situation, you will basically be able to estimate again. So normally what people will do is they run this in some sort of multi-well format. And so maybe a 96-well play or something like this. And then they will basically try to find a dilution such that half of the wells are being infected. So because they don't form this plug, so one of the things they will look at is what people call a cytopathic effect. Means by looking at the morphology of the cells. So a lot of times, if they get infected by the viruses, so if they show some of this cytopathic effect, you can look under the microscope. But looking at the cells, you can tell, okay, yeah, the cells are being infected. So in that situation, that also gives you a ways, although we cannot form this individual plug, and but by looking at the morphology of the cell, you'll be able to tell, yes, they're viruses. And again, by looking at the concentration, that half of the wells will be, means you have to do that with certain multiplication. You don't do only one well, you have to do multiple wells. You want to find a number such that half of the wells will be affected. So that's kind of a endpoint dilution assay. And so That's kind of some of the things. And so let's look at some of the consideration for viral culture. So again, this is the most fundamental way for people to study viruses. That's how people to propagate the viruses. You want to, say, culture them. They can do isolation. You can extract the viruses after they kill the cell. They amplify more. You can get more viruses to do more testing if you want to. Of course, this is one of the more fundamental way for us to detect whether there's viruses in a particular sample. You can use it for a lot of investigation. You may use that for maybe drug screening to see whether there's antiviral drugs. So that's important tools. So some of the wholesale for coronavirus, people actually know there's some of the wholesale, I think it's from monkey kidney cells. Of course, when you do viral culture for some of the very infectious viruses, so like coronavirus, the COVID-19 we're dealing with now, so we actually require some very biosafety. So we actually require high-level biosafety facility. So the one actually required to, if you want to culture viruses, coronavirus, actually it requires biosafety level 3. It's very high standard. Most of the research lab in our department, they're biosafety level 2. But very powerful about this technology is not technology, it's kind of fundamental method, is to do quantification. Because right now we have a way to quantify the number of viruses in the original solution. So if you run the plug assay, so that unit is called plug forming unit, instead of how many plugs you see. So that actually gives you an estimation. Instead of say calling virus per mil, they actually call PFU per mil or per certain volume. So because at the end, what they tell is this is not only a virus, it's a virus that actually forming a plug. And so that's the infectious one that they do. So that's why they call PFU. If you do the endpoint dilution assay, the unit they normally talk about is called 50% tissue culture infective dose. So that's a dilution that you have done such that you infect half, 50% of those tubes. That gives you a more statistical estimation of the viral concentration you have. So that's called TCID 50. So of course, something to consider is this test are not really suitable for rapid diagnostics. Again, you need to actually do viral culture. You need to have culture facility, especially for some of the very infectious ones we're dealing with. You actually require a high level of BSL, biosafety level laboratory. And so it also is quite time consuming because it takes time for the virus to infect the cell and then kind of infect the cells nearby. Depends on which assay. We can talk about days and maybe even weeks before we can see all the effects. So what's that meaning? Means it's actually not suitable for rapid point of care diagnostics. For the current situation we're dealing with, we really need something that's fast. Somebody go to the testing facility and we actually want to know this patient actually is positive for COVID-19 or not. So that's kind of another very important consideration. Again, this is a powerful method, it's a useful method, but it's actually not suitable for, as a rapid diagnostic test. So I think that kind of gives us some of this viral condition. And let me see. So let me see. I think I have this the time I have for today, and so I will talk more about other viral detection method in our Wednesday lecture. And so let me see. So let me. Do we have any questions? So before I end the lecture today. So if not, I'm going to separate the live lecture and the office hour. So if because I know some of your classmates have other classes, they may not be able to stay longer. So I'm going to end this session, but I'm going to open up my office hour right away. Okay, so we have any questions? If you have questions, post it in the chat room. Try to answer that, or you can ask during our office hour. No? All right, good. So I will see you in the office hour. Thank you, guys.